All right, in this video, we are going to talk about the material in section 8.1 from our book, and it is about estimating a population mean. So, in more general terms, what we want to do is oftentimes estimate population parameters, of which the population mean is one of those parameters, right? But it could be standard deviation or any other type of parameter. Okay, so we have a population and we want to know, what the value of that parameter is. Okay, and if the population is small, what you can do is just take a census, right? In other words, get information from every single person in your population, right? Or whatever the population is, and then compute the parameter directly. So, for instance, we might take a census and get the value that we take data from everything in our population, and then just calculate, say, the mean or the standard deviation, right, by the formulas that we talked about earlier in the course. The issue, though, right, is when the population is really big, then a census is impractical. It takes a lot of work and effort to do that. So what we'll do in that case is to take a sample, and then we'll use that sample statistic to make estimates about the population parameter. Okay, so that's a general situation. And in this section, we'll focus on finding an estimate for the population mean by looking at the sample mean. Okay, all right. But it is a more general process than that. All right, so the first kind of estimate that we have is called a point estimate. And so a point estimate of a parameter is the value of a statistic used to estimate the parameter. And remember, when I say statistic, that means it comes from the sample, right? Parameter means it comes from the population. So, all right. In this example, it says in the article, the eastern cottonmouth at the northern edge of its range. Blem and Blem examined the reproductive characteristics of the eastern cottonmouth, a once widely distributed snake whose numbers have decreased recently due to encroachment by humans. A simple random sample of 44 female cottonmouths yielded the following data on number of young per litter. All right, and so here's the data. Okay, and so we take the sample mean, right? And I'm not going to work through that, right? But you would just add all these up and divide by how many you have. You get 7.75. Okay, so that's the mean of the sample. And then that would give us a point estimate of the population mean. We would think, okay, if we constructed this sample by taking a random sample and then did a large enough sample, that the sample mean should be pretty close, right, to the population mean. Okay, and so remember, this is the symbol, right, for bar X, or X bar is the symbol for the sample mean, and mu is the symbol for the population mean. So point estimate is not really the best estimate, right, because it could vary from sample to sample, as we have already seen. Okay. Generally, what we want when we use one of these point estimates or any kind of estimate here is that it be what's called an unbiased estimator. Okay, and so a statistic like the sample mean, right, is called an unbiased estimator of a parameter if the mean of all its possible values equals the parameter. So if you remember back in section 7.2, if you watch the video from there, I wrote a computer program, and that computer program calculated all possible samples from a finite population, right? And then so I did every possible sample from a finite population of size 5, and I got the sample mean, and then I calculated the mean of all the sample means, right? And we saw that came out to be exactly the same as the population mean every time. So that's what they're talking about at an unbiased estimator, right? So if that's not true, right, then in other words, if all possible values of the statistic, right, the mean of all the possible values doesn't come out to be the value of the parameter, then it's called a biased estimator. Okay. And ideally, what we want, right, we want the statistics that we use to estimate the population parameters to be unbiased. Okay. So in other words, if you take all of their means, right, it comes out to be the mean of all possible values. It comes out to be the mean of all possible values or it comes out to be the same as the population parameter. And we also would like it to have a small standard error, right? And by standard error, they're talking about the standard deviation of the statistic. I have sample mean here, but it also applies to any other sample statistic that you have. Okay. So like I said, in section 7.2, we had an illustration that showed that this was true, right? That the sample mean, or seemed to indicate, right, that the sample mean was an unbiased estimator of the population mean. Okay. Okay, so whenever you take a sample statistic, right, it is not usually equal to the population statistic. We also showed that in 7.2, right, when we took, or in section, could have been in section 7.1 or 7.2, right, where we took some samples and we showed that, we took the sample mean and showed that it wasn't equal to the population mean in any of the cases for one sample in particular, right? If you take the mean of all the sample means, then it was equal. But lots of times, right, the sample statistic is not going to equal the population parameter that you're trying to estimate, right? And so there's sampling error, right? And any point estimate that you make, right, really is not good in and of itself, right? It always should be accompanied by some information regarding the accuracy of the estimate. Yeah, okay, we can take a sample and we can take the mean, but how accurately does that reflect what the population mean is? All right, so the number in and of itself, right, is kind of useless unless we have a good handle on what the sampling error is and how accurate our estimate is. And you're just not going to get that with a single number, right? So that brings us to a confidence interval. And what a confidence interval is, right? It is an interval of numbers. It has a lower limit and an upper limit. Okay. And so it's basically a range of numbers where your population parameter might be. Okay. So just as an example, if I have a confidence interval for a population mean, mu, it's calculated to be 11.9 and to 16.7, let's say. Now, don't focus on how did I get these numbers. I just made them up. I'll show you in a minute, right, how to construct these confidence intervals. But this is what I'm talking about. A point estimate is where you would just say this was the sample mean, right, or whatever number. But a confidence interval is where you say, hey, the mean, population mean mu, is probably in this range from 11.9 to 16.7. All right, so it's a range of numbers as opposed to a point estimate, which is just one single number. All right, so the interpretation of this confidence interval would be that the population mean is probably in the range from 11.9 to 16.7. Okay. And now you may say, probably, well, what do you mean by that? What do you mean probably? Shouldn't it be in here? And the answer is we're not guaranteed 100% that it's going to be in this range. We just don't know, right? If you take a sample, you're not taking into account every single value of the population. So you just don't know exactly if it's in this range or not, okay? We will see later on, we will attach a confidence level to our confidence intervals. And that confidence level will give us the probability, right, that the mean is in this range right here. Okay. So confidence interval is generally going to be more reliable than a point estimate. All right. Again, don't focus yet on how I came up with these numbers. I will show you how that goes. All right, so I want to construct a confidence interval for a parameter. The structure of these confidence intervals, right, is number one, that the statistic used as a point estimate for a population parameter is going to be halfway in between the lower limit and upper limit of a confidence interval, right? So we will start off with a statistic, right, that comes from a sample. We're going to use that to generate a confidence interval for the population parameter, right? And that confidence interval consists of a lower limit and an upper limit, right? Like we saw in the previous slide. And the statistic that we use, right, for the point estimate is going to be halfway in between the lower limit and the upper limit, okay? All right, and so the margin of error, right, and this is the definition that we'll use for margin of error, it's equal to half the length of the confidence interval for the interval estimate. So let's take a look at, let me just get this to where I can draw on this. So let's say that we are after a estimate for a population mean, mu, okay? So the point estimate that we would use is the sample mean. So we would take a sample, and the sample mean has a lot less observations here, and we calculate the mean, right? Add up all the numbers and divide by the sample size, okay? So again, I haven't shown you how to construct these confidence intervals yet, but we talked about what the form of the confidence interval is, right? It has a lower limit right here and an upper limit. So whatever those numbers come out to be, the sample mean is going to be right smack in the middle of the confidence interval here. Okay. So the distance from the mean to the upper limit is the same as the distance from the mean to the lower limit right here. And so we will know that this population mean is probably right somewhere in this range. Okay. And that will be our confidence interval estimate. So the margin of error, right, is defined to be half the length of the confidence interval estimate. So in other words, the distance from the lower limit to the sample mean is the margin of error. And that is also, if I take the distance from the sample mean to the upper limit of the confidence interval, that is also going to be the margin of error. Okay. And that distance, the margin of error, is an indicator of the accuracy with which a sample statistic estimates the unknown population parameter. So the smaller the margin of error, right, then the more accurate our estimate of the population parameter is going to be. Okay. In other words, if I have a really small confidence interval here, right, if the upper limit, lower limit, and upper limit are smaller compared to another confidence interval, this is going to be more accurate. And you can see here the margin of error, the distance from here to here and here to here on this confidence interval is a lot smaller, right, than this one right here. So knowing that the point estimate is right smack in the middle of the confidence interval tells you that the lower limit, right, for a confidence interval is going to be whatever your point estimate is minus the margin of error. Your upper limit is going to be the point estimate plus the margin of error. So that's how these confidence intervals, their format is. Okay, I still haven't shown you how to come up with the margin of error or the lower limit or upper limit or any of that stuff, right? So again, don't focus too narrowly, like how do I do this? How do I do this? How do I do this? I will show you, right? But it's important to understand what the structure of these confidence intervals look like. The point estimate, right, the thing that comes from the sample is right smack in the middle of the confidence interval, and then the upper limit is going to be, whatever the point estimate is plus the margin of error the lower limit is going to be the point estimate minus the margin of error. Okay. Oops. All right, so in this example, let's say I am estimating a population mean mu, and I take a sample, I calculate the sample mean to be 14.3. All right, and then I calculate the margin of error to be 2.4. Again, I haven't shown you how to do that yet. But if I have the sample mean and the margin of error, then it's really easy to find the lower and upper limit for the confidence interval, right? It would be the sample mean minus the margin of error, and to the sample mean plus the margin of error. So we would say that the sample or the population mean is probably right in this range right here, 11.9 to 16.7, based on the sample. Okay, so I keep saying probably. If the population mean is probably in there. So that brings us to the idea of a confidence level. A confidence level is the confidence we have that the parameter lies in the confidence interval. That's why I keep saying probably, right? It's not guaranteed that the population parameter lies in that confidence interval. Okay, it's not 100% guaranteed. So normally when you go about finding a confidence interval, you will specify the confidence level before you start finding the interval. Okay, and so some common confidence levels are 90%, 95%, and 99%. Okay, and so when you calculate a confidence interval with a confidence level of 90%, right? You know how I keep saying probably, right? That means that if the confidence level is 90%, that means that there's a 90% chance, right, that the population mean is in the confidence interval. Or if you calculate a 95% confidence level with a confidence interval, then there's a 95% chance, right, and a 99% chance, and so on and so forth. Okay. All right. Again, it's not guaranteed that the population parameter, right, lies in the confidence interval, but when we have these confidence levels attached to that, this will give us the probability that our population parameter lies in that confidence interval. Okay, so let's say we have a confidence interval of 11.9 to 16.7. with a confidence level of 95% for some population mean, mu. Okay, so what that means is that the probability that mu is in between the number from 11.9 to 16.7 is 0.95. Okay. In other words, there's a 95% chance that the mean includes here. Okay. And that's about the best we can do, right? We can't say 100% based on a sample where the population mean is. The only way we can say 100% is to find the values for every single thing in the population. In other words, take a census and then calculate the population mean directly. But that kind of defeats the purpose, right? That may be not feasible to do. So if you take a sample, there's always going to be some, sampling error involved here. So we can never get this number to 100%. The only way we could get it to 100% or probability 1, is to take a census, which is, again, not what we want to do here in this situation. All right, so a confidence interval estimate is a confidence interval, right, together with a confidence level. So a range of numbers where you think the population parameter is and an associated confidence level. That gives you the probability, right, that the population parameter is in that interval that you constructed. Okay. All right, and so what I was talking about before is pretty much a general situation. We can do this for lots of different population parameters, like the standard deviation, but we are only going to focus on the mean, okay, when we construct these confidence intervals. So the situation is we want to construct confidence intervals for the mean right, using the sample mean. So the confidence interval for a population mean mu, again, we're going to use the sample mean as a point estimate for the population mean. And so our confidence intervals are going to look like this. The lower limit is going to be x bar, the sample mean, minus the margin of error. The upper limit is going to be x bar, the sample mean, plus the margin of error. Okay, so this is that information from before applied specifically to population means and estimating the population mean with the sample mean. Okay, so that brings us to example 8.2. In example 8.2, I am going to show you how to construct a confidence interval, right? We're going to get a 95% confidence interval for the population mean, assuming that we are given the population standard deviation, okay? So now you may say, well, if I don't know what the population mean is, how am I supposed to know what the population standard deviation is, right? Don't you need the population mean to calculate the population standard deviation? And the answer is yes, you do, right? So this is a little unrealistic, but it is a good starting point for talking about the situation where you don't have the population standard deviation. All right, we will do that in section 8.3. Okay, so I always found that a little strange. How are we supposed to know the population standard deviation if we don't know what the population mean is? But yet we're finding confidence intervals. But this is just, again, sort of the first step to getting towards a more realistic situation where we don't know, right, what the population standard deviation is. Okay, so in this example, what I'm going to do is going to show you how to construct a confidence interval. And this way is the only purpose here is to kind of illustrate the idea of how we're going to do that. So we're going to work through this one time this way, okay? And then we will take a look at the formula for the confidence interval. And so I'm only going through this process to show you, to illustrate why the formula that we're going to use later works and gives you a confidence interval, okay? So don't feel like you have to do it this way, all right? In section 8.2, where we calculate a lot more confidence intervals, then we're just going to use the formula, right, for the confidence interval. But in this example, I'm basically showing you, where that comes from, okay? All right. It says the U.S. Census Bureau publishes annual price figures for new mobile homes and manufactured housing statistics. The figures are obtained from sampling, not from a census. Okay. A simple random sample of 36 new mobile homes yielded the prices in thousands of dollars shown in table 8.1. All right. So here are here's the data set, right? And we want a 95% confidence interval for the population mean. So that's our confidence level. Okay. And so we are assuming or given that the population standard deviation is 7.2. First off, right, to build a confidence interval, we know, right, that the confidence interval is given by this, right? And so it's going to be x bar minus the margin of error, x bar plus the margin of error. So we need to calculate x bar. I already did that, right? We would add all these numbers up and divide by how many you have, which is 36, and we would get 63.28 for the mean, okay? All right. So now the next thing is we would consider the confidence interval, or the confidence level rather, right? And we want a 95% confidence interval, right? And so what that means is we would go and consider the normal distribution here, right? And look at this area underneath the normal density curve, right? Where the area in the middle is 0.95, okay? So Um, all right, so the area in the middle here is 0.95. And so if the area in the middle, right, we want to know what is 0.95, what we want to do first is figure out what are these z-scores here. Okay, so these z-scores here that trap 0.95 in the middle. And if you think back to section 6.2, we talked about how to do that. So if this area here in the middle is 0.95, right, that means that the shaded area, right, over here and here is 1 minus 0.95. Which is 0.5, or 0.05 rather. Okay, so the shaded area here and here. If this area is right in the middle, right, we know from the symmetry, right, of the normal curve that this area to the right over here is half, right, the area, this combined area. So this area and this area are 0.05 together. So if I take 0.05 and divide it by 2, and we're dividing by 2 again because we know that this area here and this area here are exactly the same, we get 0.025. Okay. All right, and so then we would go to the table, right? Table 2, and look up, right, an area of 0.025, and that would give us this z-score over here. Okay. And because of the symmetry, we would know that this z-score over here would have exactly the opposite, right, z-score as this one over here. All right. So if you think about it, this z-score over here, another thing that I want to say, if you remember the notation, right, of z of 0.025. Okay. If you remember what that was from chapter 6, right, that is the area, that is the z-score that has an area of 0.025 to its right. Okay. And so that would be exactly this z-score here, right? And that's going to be important because we'll see that notation later when we come up with the formula for the confidence interval. Okay. All right, so we would go to the table and look that up, and if our confidence interval was 90, then we would do the same calculation, 1 minus 0.90, and then divide it by 2, and then go look that up, right, in table 2. That's going to give us this z-score here, and because of the symmetry of the normal curve, we would know that this z-score over here is the opposite of that one. All right. So I'm not going to do the lookup. I'll just skip that part, right? But I'll tell you what you should get when you look that up. We would get that that left one is minus 1.96, and over here, right, we would get 1.96 for the z-score. Right? So those are the z-scores that trap an area of 0.95 in the middle, and that's what we want, right? Because that's our confidence level. All right, so we find those z-scores. All right, so what we know, right, is that 95% of the data will fall within that range from a z-score of minus 1.96 to 1.96. And really what that is, that range is actually the confidence interval, right? But it's expressed in terms of the standard normal distribution. Okay? And what we want to do, all we really need to do is to go back and express that confidence interval in terms of the sampling distribution of the sample mean. All right? So that is, remember, right, the sampling distribution of the sample mean is right, mu of x bar, that's the mean of all the sample means, that's equal to the population mean. And sigma of x bar, standard deviation of all the sample means, is equal to the population standard deviation divided by the square root of the sample size. All right, so we'll need to figure out what these are. The problem here is that we don't know this, right? We're not given the population mean, so we don't know that. If we knew what the population mean was, then there's no point, right, in constructing a confidence interval, because we know exactly what it is, right? But we don't, because we only took a sample. These, remember, we were given, right, that the population standard deviation, so we know what this number is, so that's good. And we know that the sample size is 36, right, because we were given that all. So we know these, right, and that's good. But we don't know this, all right? Okay, so now, again, all we need to do, right, is to express these z-scores, right, in terms of the values of the sample mean, all right? So if you remember the z-score formula, right, z equals x minus mu over sigma, okay? We're going to use this formula to work through that. We do need to adapt that formula for the sample mean, because that's what we're talking about, right? So it would be z equals the sample mean, x bar, minus the mean of all the sample means divided by the standard deviation of all the sample means, right? All right, and that brings us back, right, to the sampling distribution of the sample mean. We know that the mean of all the sample means is the same as the population mean. Again, we don't know that. The standard deviation of all the sample means is the population standard deviation divided by the square root of the sample size. So we're going to plug these things back in here. And our formula is going to become this. All right, so it's going to be z equals x bar minus the population mean, so sample mean minus the population mean, divided by the population standard deviation divided by the square root of n. So we have a bunch of this information, right? We know that the z-score is 1.96, so we put 1.96 in for z down here. We know that the sample mean is 63.28, so we can put that in here. We know, well, we don't know, right, the population mean. We weren't given that, so we do not know that. We are given that the population standard deviation is 7.2, and we're given that the sample size is square root of 36, which is just 6. So all we need to do now is to use a little algebra to calculate, solve for mu in this, and we'll get 60.928. So let's take a look at how that's done. Okay, so the first thing I would do is multiply both sides by this expression right here, 7.2 divided by square root of 36. Multiply this side, right, by the same value. And even though my writing's big, this is really over 1, right? So on this side, these things are going to cancel out. And so what I'll get, and I'm have to move up here, is that 7.2 times square root 36 times 1.96 equals 63.28 minus mu. All right, next up, I would subtract 63.28 from both sides. So over on the left side, I would get minus 63.28 plus 7.2 divided by square root 36. That equals minus mu. All right, because on this side, the 63.28s cancel each other out. So next, I would multiply, I want to solve for mu, right, not minus mu. So I would multiply everything by minus 1 on both sides. On the left side, right, this negative 1 would get distributed through the parentheses. And so I'd get 63.28 plus 7.2 divided by square root 36 equals mu. Okay. So that's what we would get right here. Okay, when we solve for mu. So, sorry, not minus, right? It would be not plus, right? But minus right here, sorry. Right, because when you distribute the negative 1, this is positive, right? And that changes that to negative, okay? So what we've got here, right, is really the lower limit of our confidence interval when we do that, right? If you think about what this is, what is 63.28? It is the mean, sample mean, rather, minus. And it turns out, right, that, oops, I dropped a little piece right here. Sorry, I'm going to go back and fix that. So here, I forgot to tag the times 1.96, sorry. So this part over here is the margin of error. Okay. If you take that into the calculator, (63.28) minus 7.2 divided by square root 36 times 1.96. You see I get 60.928, right? Which is this number right here, okay? Okay, so again, just a little algebra, right, to get to this. Again, this is the first time that we're going through this. After I get done with this example, I'm going to show you the formula, right? And so if you use the formula, then you don't have to go through this algebra every single time, okay? All right, so that is going to be our lower limit for the confidence interval. All right, next up, we're going to do exactly the same thing, right? We're going to do it for the other z-score that we have, which is minus 1.96. All right, so we put that in for z. X bar is still the same. Sigma is still the same. 36, right, is the sample size still. And so we get this equation. Okay, and then we can run through those steps again. Multiply both sides by minus 1.96. Minus 1.96 times 7.2 divided by the square root of 36. That'll get rid of this number and move it up here. Then subtract, right, 63.28 from both sides. Then multiply it through by a minus 1. So I get 63.28 plus 1.96 times 7.2 divided by square root 36 equals mu. All right, and punch that into the calculator. That's going to be our upper limit for our confidence interval, right? And so that is 65.632. All right. So we have the lower limit and we have the upper limit. And this is a 95% confidence interval for mu, right? So what that's saying is that the probability that the population mean is in this range from 60.928 to 65.632 is 0.95. In other words, right? There's a 95% chance that the population mean is in this range right here. Okay. All right. In pictures, it looks like this. Remember, we had minus 1.96 and 1.96 here. And we know that the mean is right here at the middle where the hump is, right? And here's our upper limit and here's our lower limit, okay? So the margin of error, I already told you the formula for it. It was that 1.96 times 7.2 divided by square root 36. That's the formula that I'm about to show you. And remember, originally I said that the margin of error is the length of this interval divided by 2. You can also get it that way, right? So if I take the upper limit minus the lower limit and divide by 2, that will also give me the margin of error. So in some of the problems in the book, they ask you to calculate the margin of error both ways, right? As the length of the interval divided by 2, and also using the formula that I'm about to show you. Okay. All right. So there's our 95% confidence interval. So now, again, what I said before was I just showed you this process, right? Basically once. So hopefully you can get a better understanding of why the confidence interval gives you what it gives, right? And so now what we're going to do is basically use the same steps I showed you, right, to come up with a formula, right, for the confidence interval. So if you think about what we did right here, right, what we did was we started with this formula for z-scores, right? And if I multiply both sides by sigma divided by square root n, and then solve for mu, right, going through those same steps, subtract the sample mean over, multiply through by minus 1, I get this formula right here. Okay, I get bar x minus whatever the z-score is times the population standard deviation divided by the square root of n. Okay. All right, and so now I'm going to use that formula to get a formula for the lower limit and a formula for the upper limit and for the margin of error. To do that, right, to be more specific about what the z-score is, I need the confidence level. So if the confidence level is 1 minus alpha, then the z-score that we need is z of alpha over 2. Okay, so that just to show you and run through that again, why it's z of alpha over 2. If we do that again, remember in the previous example we had a 95% confidence interval, right? So 0.95, right, was our confidence level. And then we did 1 minus. We did 1 minus 0.95. That's going to give us 0.05. So this would be our alpha. All right, so this is our confidence level. Next up, we would find our alpha, which is 0.05, and then we would find alpha over 2. And we would get 0.025. And then what we would need to do is to find z of alpha over 2. So you can see down here in the formula for the lower limit, for the upper limit, okay, I have z of alpha over 2. All right. So the purpose of these formulas, right, is so that you don't have to go through the algebra that we did in the previous example, right? You can just find these values in your problem and then use these formulas, right, to calculate this out, okay? And so now, why is it z of alpha over 2? Well, remember, right, what we wanted for a 95% confidence interval, right, was we wanted 95, our confidence level, we wanted 95%, like right in the middle here, right? 0.95. All right, that's what we wanted. And so if 0.95 of the area, right, is right in the middle, that means that there is a total of 0.05 on the ends. In other words, if I take this part over here and this part over here, right, and add those areas together, I'm going to get 0.095 because we know that the total area, right, is 1. And then what we want to do, right, really we want to find this z-score right here, what that z-score is. And we know that the piece to the right of the middle and the piece to the left of the middle have exactly the same area, right? And so if that's true, then the area over here to the right is 0.05 divided by 2, right? Because half's over here, and we get 0.025. So that is the area over here, okay? All right, so this formula gives exactly, right, the z-score that you need to find, okay? So that's why we have z of alpha over 2 here. And just to recap, how do you find that? You take your confidence level, you subtract that from 1, that gives you alpha, right? And then you divide it by 2, and that will give you, right, if you find z of alpha over 2, that will give you this upper part right here, okay? Or the z-score where, you know, it has an area of alpha over 2 to the right, okay? So that goes in there. All right, so these are the formulas that you should be using to work the problems in section 8.2 when we're actually constructing confidence intervals. Do not do it the way I just showed you, right? I just wanted to go through that once so it doesn't look like, you know, magic. Oh, you just do these things and boom, out pops your confidence interval, right? I at least wanted to give you an example where I showed you that, you know, this construction of the confidence interval is connected to the things that we talked about in chapter 7 and in chapter 6. Okay, so because to me, if you understand, you know, those things in chapter 6 and chapter 7, it helps you understand where this confidence interval came from. All right, but don't use these in section 8.2 and on the tests, right, or on the quizzes. This is just going to be, you know, just cut to the chase and use these formulas to calculate your confidence intervals. Okay. All right. All right, so just a little bit about the margin of error. The margin of error, right, is going to depend on the sample size and the confidence level. In also the population standard deviation or the sample standard deviation. In section 8.2, we will talk about exactly how margin of error and sample size are related. and how the confidence level and the margin of error are related to each other. All right. So this technique I've showed you and those formulas I've shown you are good when we know the population standard deviation. So essentially, we're going to be constructing two types of confidence intervals. One where you know the population standard deviation. That's going to be in section 8.2. And then in section 8.3, we will have to develop a new technique. And those problems are going to be where we do not know the population standard deviation. All right. Finally, the last slide in here just shows that if you take a different sample, right, of size 36, and this is a different sample, in this example we got 6.583, whereas before it was 63.28. So here I'm using a different sample, all right? And if I want to find a 95% confidence interval, right, what I would do is take the mean. In this case, you can see that the mean is different than what we had before. This time it's 65.83, and before it was 63.28. So take a different sample, for a different sample, this is probably going to be different. If we're doing a 95% confidence interval and the rest of this stuff is the same, in other words, the standard population standard deviation is the same as the previous example, and the sample size is exactly the same, then the margin of error is going to be exactly the same, 2.352. So the confidence interval would be the mean, right? Sample mean minus the margin of error to the sample mean plus the margin of error. And you can see we'll get a different confidence interval for a different sample. So the confidence interval is going to change potentially from sample to sample as well, okay? So it's not like there's one confidence interval, right? For every sample that you take, you can get a confidence interval, all right? And so that kind of leads into this simulation. In this simulation, basically what they did was take 25 different samples. So you can see over here are the sample means. So the sample means are different. Here they constructed a 95% confidence interval, right, based on this sample. And so you can see the confidence intervals are illustrated over here. So for like this first sample, here's the confidence interval. It goes from 63.05, right, to 67.85 up here. And here they have the green dot, right, indicates the sample mean. So 65.45. So in that case, the population mean, they say here, is 65, right? You can see that 65 is in between, right? Those two lower limit and the upper limit here. So here's it for another sample. You can see it's a different mean, sample mean, a different confidence interval, but this one still includes the population mean 65. All right, and so you can see that all of them do except for this one down right here. In this sample, right, the sample mean was 67.73, right, and the confidence interval then will be 65.33 and 70.13. All right, and so you can see that sample population mean is not in that confidence interval here. So again, it's not 100%, right, that your population mean will be in your confidence interval. That's where the confidence level comes in. You can see not all of them will be, right, but a lot. And in fact, if we did it for every single one, right, we would see that 95% of those, right, of the confidence interval would include the population mean. All right, and the only way, whenever I took this first, I was like, well, I don't want to be 95% sure. I want to be 100% sure, right? But you can't be 100% sure. The only way to get 100% is to take a census, right? Find the data for every single item in the population, and that defeats the purpose, right, of doing this. You can't do that in every situation. It's just not feasible. Okay. All right, so about the problems in this section, I'm not assigning any practice problems in this or any homework problems in this section because of the fact, really, this is just kind of illustrating the concepts of the confidence interval. So this is more of an explanation video than anything else. In the next video about section 8.2, we will sit down and start the business of constructing these confidence intervals using those formulas that I've shown you. All right.